Okay, now we want to use our logical gates to implement all of these functionalities in the ALU of 8085 microprocessor. The first functionality is, and we want to see how it is implemented in 8085. So here we said that the combination of a NAND gate and a NOT gate is an AND gate, and the truth table of an AND is like this, that the output is 1 only when all inputs are equal to 1. And you see that it looks like that we have two 8-bit values, and the corresponding bits of each of the 8-bit values are ANDed together, A0 with B0, A1 with B1, A2 with B2, and so on to A7 with B7. We could just bring up the related wires of A and B in this format, so this would be A0, this would be A1, and this is B0, B1, and so on, so that we could see that this is the 8-bit A and this is the 8-bit B, and all the corresponding bits would be ANDed together, and therefore we could create another abstraction. Just put this into a rectangle and say this abstraction is an 8-bit AND, which would take two 8-bit inputs, A and B, and the output would be again 8-bit. So this is out 0, out 1 to the value of out 7. Now, one thing that I wanted to mention before I explain everything, I first think to myself that if I want to just explain it in a general format, it's better that I don't create it, because people could just look at the Wikipedia or other public lectures to find it out, so to just understand the subject. So the best way for me, or the motivation for me to create any lecture, is to give you an intuition, something that you can just learn by just reading or studying other lectures. So the intuition about this would begin from here, because a lot of you might know what an AND gate is. We have 9 different instructions in 8085 which use the underlying hardware that we explained to execute the AND instructions. These 8 instructions are like this. ANA, A, B, C, D, E, H, L, and M are 8 of them alongside ANA byte, NI byte, meaning that ANAA, it means that I want the values of the A register. We know that we have 7 8-bit registers called A, B, C, D, E, H, and L. So ANAA means that I want the contents of A register to be ANDed with itself and the result to be saved in the A or accumulator or the 8-bit A register again, which we explained in the previous lectures in the architecture of 8085. ANAB means that I want the contents of the A register to be ANDed with the B register and the result to be saved again in the accumulator or in the A register again. ANAC means A to be ANDed with C and the result again in the A, meaning that the destination and one of the operands is always the A register. And this would go on until for all the 8-bit registers. M I will explain in the rest of the lecture. But what about the A and I byte? This means that a byte would be provided here, like for example B7H, meaning that this is a value in the hexadecimal, which would be 8 bits. Again, every hexadecimal digit is 4 bits. So this means that I want the contents of the A register to be ANDed with the value of B7 that we provide as part of this instruction, and the result again to be saved in the A register. It means that we could change our abstraction in this way, that we say one of the inputs of my 8-bit ANDer is always the A register, and the result is also saved always in the A register. The other input could be brought from any one of the other 8-bit registers or even the A itself, and well, it's just like that. Now, you might say, one thing that you might say is that we know that the computer only understands zeros and ones. So what is it that we say A, B, C, or D? So you see, every register in the 8085 would be assigned a value. Since we have 7 registers, we use 3 bits to assign a value, or 8085 uses 3 bits to assign a value to the registers. Meaning 3 zeros is saying that this is B register, 001 is for C register, 010 up to 111, which would be the A register. In other words, we say that the opcode of the ANA instruction is equal to 10100, and the other 3 bits would specify one of the 7 registers alongside M. It means that 1010000, it means that I want the value of the B register to be ANDed with the A register and result to be saved in A. In other words, if in the 8085 microprocessor we said that we have an 8-bit register called the IR register. If the value in the IR register is equal to this value 1010000, what the 8085 microprocessor does is that first it loads one of the inputs of the 8-bit ANDer with the accumulator with the A register, and it loads the other inputs with the B register. It would execute the AND instruction and would save the result in the A register again if it sees this pattern. So we could just write all the 3 bits for other registers, meaning that 10100, so this is the opcode. We will explain later about what the opcode is, but for now, if we see, this is the opcode of ANA. So 101000001 means that I want, in hexadecimal it is A1, means that I want the value, the contents of the A register to be ANDed with the C register 001. These 3 bits are for C register, and the result to be saved in the A register. When we say that I want, it means that if these patterns of zeros and ones is seen in the IR register, the 8085 microprocessor would, as we said, load the corresponding register is one of the inputs of our 8-bit ANDer and load the A register in the other input, do the ANDing, and would save the result in the A register again. So one thing we should also note is about the M. What is M? You see, the opcode for ANA is always, all of these ANA, A, B, C, and D is for us to communicate better, but the computer always understands zeros and ones. We say the opcode for ANDing is always 8 bits long. If this pattern is equal to 101000110, it means that the instruction is ANA M, or I want the contents of the A register to be ANDed with a location in memory. But what is that location in memory if we are not providing that value in the instruction? That location is pointing by the HL. It means that if this value is in the IR register, what the 8085 microprocessor does is that first it looks at the register of HL pair, which would be equal to 16 bits, right? Each one of these is equal to 8 bits long. So it would put the 16 bits of the HL register pair and put that on the address bus. It would point to a location in memory, right? Then it would go into that location in the memory. We know that the address of every memory location is 16 bits long, but the memory location would have 8 bits of value. So after it puts those 16 values on the address bus, and therefore choosing one of the memory locations, it would fetch those data, those 8 bits data, and put those 8 bits data in the other input of 8-bit ANDer, and we know that the A register would always be loaded in one of the other inputs of the 8-bit ANDer, and the result would be saved in the A register again. So this means the ANAM. The other instruction is ANI byte, that, as we said, the byte would be provided directly in the instruction. So these 8 instructions, the length, as we said, is equal to 8 bits or 1 byte, but this one would be 2 bytes. So, for example, if we say ANI B6H, it means that I want the contents in the A register to be ANDed with the B6 value, and the result again be saved in the A register. Now we want to also use one example here. Let's say that we have the value of 1010000 in the IR register. Or in other words, you as the programmer, you have put this value in a location in RAM. The CPU, the 8085 microprocessor, has fetched this instruction, put it inside the IR register. Now what it does is that the 8085 would look at the contents of the B register. It sees it is equal to 17H. 17H in binary is equal to 0001, which is 1, and 0111, which is 7. So it puts it in one of the inputs of the 8-bit ANDer, and it also loads the other input of that 8-bit ANDer, which is part of the ALU, with the value in the contents in the A register, which is equal to B6. Just imagine it's that. B6 in the binary is equal to this one. And then that 8-bit ANDer would do the calculation exactly based on this truth table. So 0 and 1, it is 0, right? 1 1, it is 1 1 1 1, 0 1 1 1 1 0 0 0 0. The result in binary is this, and in hexadecimal it is 16H. So it would save this value back in the A register. The A register content was already B6. Now it is equal to 16. That was the result of the execution of ANAB in the human readable form, or 10100000 in the binary form, or A0 in the hexadecimal format. So I just wanted to give you this intuition that every instruction that you see has an underlying hardware, is using an underlying a part of the hardware of 8085 microprocessor to be executed. These 9 instructions, they use this part of the ALU. This would be a part of the ALU that then when we complete our ALU, we would show it to you how it is just inside that ALU. But all of these 9 instructions, these 9 different bit patterns, they would use this part of the ALU to execute the AND instructions. Now, in the next lecture, we want to implement other logical instructions, but it would be in a much faster speed.